Hello and welcome to lecture number 3. In this lecture, we will cover the fundamentals of this language, mainly the cover group and the cover point. Okay, let's start with the basics of a cover group. If you look at this particular block, what I'm doing is first you have to declare a cover group with the keyword cover group. And you also need to provide it with a name, a label, so to say, and it is required. You cannot omit the name, and then you also need to provide it with a sampling edge. This sampling edge is when the cover points and bins of these cover groups will be sampled, or in other words, evaluated to see if they have been covered. So the sampling edge is required. But in case, let's say, you omit the sampling edge, then you have to procedurally trigger the coverage sampling using a built-in method called sample. And I will show you an example in upcoming lectures on how you can do that. But I personally suggest that always provide a sampling edge. Also, the sampling edge should be meaningful. Here I'm simply giving it a clock. That means that every positive clock evaluate to see if these cover points have been covered. But you can have more meaningful edges, as I will show you in one of the examples. So you declare a cover group, give it a name, provide a sampling edge. Now inside this cover group, you have to provide cover points for the variables of your design. And here I'm saying cover point offset. Offset is a variable, 2-bit variable. And I'm also saying cover using the keyword cover point address, which is also a variable, 8-bit wide. And you may or you may not provide labels to these cover points. I very highly recommend that you provide the labels, meaningful labels. If you don't provide these labels, then the simulator will provide its own naming convention, which I can assure you will not make much sense to you. So after you declare the cover points, you end the group with the keyword end group. And then you have to instantiate this group. Until then, the memory won't be allocated for it, and the cover group will simply sit there. So we take the cover group name, we give it an instance name, and equal to new. And new, this is a very basic way you even instantiate a class. So this is where you instantiate a cover group. Now, these are very basic points of how you get going declaring a cover group, and we'll see a lot more detail on this. One final note here is that if you do not provide any cover points in the cover group, then the cover group is basically meaningless. It's not going to cover anything. The bad part is the compilers normally don't give you any warnings or errors when the cover group is empty, because you may keep it empty for a while and later you can put some cover points in it, so the compiler doesn't want to give you unnecessary warnings or errors. So this is basically fundamentals of a cover group. Let's continue with the same cover group, and I'm only showing one variable, offset. The cover group has been defined here, and here's the cover point, offset, and you can provide a condition saying that if and only if reset is not asserted, that this cover point should be evaluated to see if it has been covered, which makes sense because during the reset, we are really not doing anything. The design is still under the reset condition. The other thing I'm showing here is 2 squiggly brackets. In the earlier slide, you didn't see those, which is fine. And I will tell you what happens if you don't put those in the upcoming slides. But if you do put the squiggly brackets, it means that you haven't specified explicit bins. Now, we don't know what a bin is, but basically a bin is something where you collect the coverage information. So for example, when I put this squiggly brackets, it basically says that create 4 automatically generated bins. Why 4? Because offset is 2-bit wide. So in auto bin 0, this is the name that the simulator will provide, because I'm not saying anything about the bins. I'm just saying create as many bins as necessary because I'm providing these two squiggly brackets. So it creates 4 bins, names them. You can name the bins yourself, as we'll see in upcoming slides. And the simulator basically says auto bin 0 will cover offset 0. Auto bin 1 will keep track of how many times offset 1 has been covered, and so on and so forth. So I have introduced you 2 new concepts here. One is the reset condition, control condition as I call it, and also a very high level view of how you can provide or ask a simulator to create explicit bins. Now here's a log that comes from one of the popular simulators. Your simulator may be different and the log may look different. But here basically the simulator created 4 auto bins, 0, 1, 2, 3. And this log shows that they have been covered thousands of times, which is rather redundant. But this is just an example. And it says that all the cover points have been covered, and hence the cover group also have been covered 100%. So at the end of the day, we need to make sure that the cover group is covered, and if not, we need to look at the bins and the cover point. In this case, everything is covered. Now let's look at an example of how we can use a cover point. So I have an enum, and I'm from the old-fashioned parallel PCI bus, so which you may or may not be familiar with. But a PCI bus has a lot of different cycle types: IAC, IO read, IO write, mem read, mem write, so on and so forth. So I have created an enum with this 12 different cycle types and give it a name PCI commands. Then I create a cover group and give it a name PCI commands underscore cover. Always give a meaningful name. And as I was just telling you, the sampling edge also should be meaningful. I could have said add pause edge of clock here, but then it is very redundant and it will slow down my simulation. So what I'm doing is always at neg edge of frame. What in the PCI world, the PCI cycle starts at the neg edge of the frame. So what I'm saying is at the neg edge of the frame, evaluate this cover point called cover point for the enum PCI commands. Here is the PCI commands. Evaluate PCI commands to see if it has been covered. And I've given it a meaningful label, which I said you should. So you can now see that how you can cover all possible cycles of this particular bus, PCI command and byte enable bus. Now again, I'm not providing it any bins because I haven't discussed bins yet, but if you don't provide any bins, simply put a semicolon there or 2 squiggly brackets as I just showed you, then implicit set of 12 auto-generated bins are created for 12 values in the enumerated type PCI commands. So basically, whenever you cover point a given variable and don't tell the simulator what kind of bins you want to create, it will create all possible bins based on the width of this variable. In this case, it's an enum time, so the number of enum values you have in this particular enum type. So it will create 12 of those. Now this is again basic of how you can start with functional coverage. Now some of you who are familiar with code coverage may say, wait a minute, code coverage also covers the enum type. So why do I need this cover group and the whole functional coverage code and everything? The answer is yes, code coverage will cover this too. But bear with me. What I'm going to do is I'm going to take the same example and then expand it and expand it further so that you will see how effective your functional coverage becomes. And that's where you will see the code coverage will fail. Some more points on cover groups. So back to the same cover group, but what I've now done is I have parameterized the cover group, which I highly recommend because you may create certain cover groups and then you can instantiate it multiple times with different values. So I have int low, int high, and bit 7 to 0 address of reference type. And I'll tell you why you need a reference type here. And my sampling edge is at pause edge of clock. Inside the cover group, I'm saying cover point address, name of the cover point. And inside this cover point, this is the first time I'm showing you some bins, which again, bear with me, we will discuss in detail. I'm saying in this ADR bin, cover the address ADR1 from low to high. And what I'm doing is, when I instantiate, like we discussed that all the cover groups need to be instantiated, I'm going to take the same cover group and instantiate it twice. And at one time, I'm going to give it 0 to 127, and I'm going to give it ADR1. ADR1 is this particular variable that we declared here. Note that in the cover group, I have a generic name called address, and that's why I'm saying cover point address. But when I instantiate, I'm going to give it the real name of the variable that's in the design. Now, the reason for the ref type is because address 1 and address 2 are variables. They are not constants. So if you have, which makes sense, you have multiple instances with the variables, then you have to declare the formal as of type reference. So that's all pretty much it here. You should, as a matter of fact, as part of your methodology, create what I call generic cover groups and then use them multiple times rather than creating a new cover group for different addresses and different low to high bins that you want to cover. So that's all, folks. This is rather straightforward. We have seen how to declare a cover group, how to declare a cover point, what's the sampling edge that you need to provide to make sure that you sample or evaluate the variables at the right time. Thanks a lot for your time, and I'll see you in the next lecture.